she's to deliver today's seminar. Mohan is one of the most creative people in the field. He's worked across the interdisciplinary field. I actually just looking at his CV and hadn't remembered that he first got his MS in engineering at Cornell, and then he went on to do his PhD at University of Queensland in Brisbane, working with Michael Nielsen at the time and Jared Milberg on topics in quantum information theory. He then went on to a postdoc at Berkeley with Brigitte Whaley, working on quantum biology and some of the new ideas relating to how quantum advantage might be seen in light harvesting molecules and photosynthesis, and then went on to join the staff at Sandia National Labs, where he's been since 2013, and currently is just been named a distinguished member of the technical staff, which is a real distinction. So congratulations to Mohan on that, well deserved. As I said, he's worked across discipline in areas we have great interest overlap in continuous measurement, in quantum control, and quantum engineering. And today he's going to tell us about quantum machine learning. Always fearless.
Classical quantum inspired.
Quantum inspired. So please welcome Mohan.
Thank you. Kind introduction. Creative was one way to put it, and scatterbrain is another way.
Yeah, I relate.
Yeah. So yeah, it's a pleasure to be here. Thank you for the invitation. It's lovely to see everybody here. So I'm going to talk about quantum-inspired geometric data analysis. I'll explain what all of that means, hopefully by the end of the talk. But I want to say that to just briefly shout out to a newly established structure within Sandia, the Quantum Algorithms and Applications Collaboratory, which is co-led by Andrew Wachewski, Otis Parrott, and myself. And we are a group of 25 plus researchers who focus on studying applications of quantum computing and quantum technologies more broadly, and then figuring out what is actually useful, what can we do with these machines, and at what time scale so most of what I'll talk about today is actually not quantum computing. So instead, what I wanted to do is just provide you a brief advertisement for some work that is quantum computing related. So the first 10 minutes or so of the talk will be kind of a lightning overview of these three papers that we put up on the archive last year or so. I thought I'm happy to talk about any of this to people who might be interested, but since the bulk of the talk is not quantum computing related, I thought I'd tell you a little bit about things that we've done in quantum computing, just as a preview. So as I said, these are three papers we put out recently. The first is focused on new methods of doing optimization for variational quantum algorithms. The second is focused on, as the title says, establishing trust in quantum computation. So when you have a non-fault tolerant device, or even a fault tolerant device, how do you establish some trust in what its output? So in most cases of utility, you don't know actually what the output should be. So how do you know whether the output that you get from a device is accurate? And the last book I'll briefly advertise is some work that we did and tightening error bounds on adiabatic evolution when you digitize it. So when you use a quantum computer to do adiabatic time evolution, we understand the error much better as a result. Okay, let me just step through each one. So the first is this work on surrogate-based optimization for BQA. So variational quantum algorithms, I assume most people are familiar with. It's this idea that you use a quantum computer as a coprocessor to output some observable, which you optimize within a classical optimization. So it's a parameterized circuit that you optimize. And the thing we're really thinking about is the classical optimization step, not so much the quantum step. And the question is, how do you do this classical optimization efficiently when the data is poor quality in state? Right? So what I mean by that is that we know that these devices are going to be noisy, so you're not going to get a perfect estimate of the observable or the cost function. And each use of the machine is expensive. It's a quantum machine, so you want to make as few calls to it as possible. Right? And so that's what I'm saying. So limited function evaluation, function evaluation is noisy, gradient and Hessian evaluations, which are kind of the bread and butter of classical optimization, are also expensive and noisy. And utility comes if variational quantum algorithms are going to be useful, it's going to be at large scale. So when you have hundreds of thousands of parameters. So how do you even think about doing optimization in such scales? It scares a lot of people doing optimization. Our proposal to do this is actually to construct surrogate models for the output of these machines. So the fact that you have a circuit that produces this output is just one parameterization of the cost function, right? You can try to learn a different parameterization by taking some training data. So you take some points. So this is a kind of a pictorial summary of what we did. This is the true objective function. It's a 2D function, it's 2 parameters. This is the value of the function color coded. What you do is you just take some random samples from this 2D plane, and then you can use something called kernel density estimation to kind of patch together the value of those functions to construct a smooth surrogate model for that construct. So the point is that this kind of looks like this, and you've extracted this by just learning of measurements at, I think this is something like 15 sample points. And so you just query the machine a few times, and then based on those few queries, you construct a estimate of the cost function that then you do optimization on this estimate. And this is a model that you can query very quickly, and it's cheap to evaluate. You don't have to do many calls to the quantum machine to do the optimization.
In this graphic, this is just illustrative. I mean, the objective function, you don't know thing on the left.
Right. So,
you're just saying if it were to look like this.
In this case, yeah, because these are simulations, I'm sampling this data from this cost function. But it's not actually sampling the cost function. It's sampling. So this is the expectation value over many shots, right? So if you had infinite shots from your machine at each one of these parameter values, this is what you'd see. But we take a finite number of shots, it's 100 shots at each parameter, each of these black parameter values. And if you just did an interpolation, you'd get this, which is like this patchy surface, which is probably not something you want to optimize over. But what you do is you use something called kernel density estimation to smooth this and recover a smooth, explicitly smooth and continuous cost function. And this scales very well to higher dimensions as well, which is what we showed. The archive reference is blocked. I don't have to I don't know how I do that.
Yeah, okay. Oh yeah.
So that's the first one. As well as the second paper I want to tell you about is this notion of establishing trust in quantum computation. So this is the generic problem that I kind of talked about. You have a computational problem. Let's say you have a quantum algorithm and associated quantum circuit that will produce some solution to this problem. In this case, it's supposed to be the ground state energy of some molecule. With ideal quantum hardware, this is the kind of output string you would get. With real quantum hardware with noise, you get something like this, right? And you're supposed to classically post-process the output to get an estimate of this energy. That's the point of this output. But when you have noisy hardware, can we trust this output? And what degree of trust can we place on this output? This is an old question that I think Ivan has thought a lot about in the context of analog simulation. But a NISC device is basically an analog device. So you have the same question in this context. Right? And the point is classical verification is not possible, right? Because you don't know what this answer is supposed to be. So how do you solve this problem? What we developed is a protocol to estimate the process fidelity of the circuit. Right? So you don't have an estimate of the state fidelity, which is ideally what you like. What's the accuracy of the output? But you have the next best thing, which is the process fidelity of the process that you ran. And the way you do it is you run a related family of circuits. So if this is the original circuit that you're running, you run, these are called mirror circuit families. So one is you run the same circuit in forward, but you run a randomized compiled version of it in reverse. And the second ensemble is you run a randomized compiled forward version and a randomized compiled backward version.
the random compiling, do you mean same gates, different order? Or what do you mean by random?
So random compiling is that first you compute the inverse of the circuit, which is just the inverse of each of these gates. You can compute that efficiently. But then you random compile it. And so randomized compilation is a way to basically you insert random Paulis at the beginning of the layer, and then you compensate that with a random Pauli layer. It's not quite random, it's a dependent Pauli layer at the output. So this is a technique by Emerson and they developed. So the reason you do that is so the intuition behind this is that the reason you do time reversal, why you do the mirror version of the circuit, is so that you know that you have a definite outcome, right? Because if you do a circuit forward and you do it backwards, you know what ideally, if everything is ideal, you know that you should come back to the state that you put in, right? But the problem with that is that you might have error cancellation that says that you might come back close to the state you put in just because the errors you induce going forward get canceled when you go backwards. So that's not the best way to estimate the fidelity. So instead, what you do is you randomize the backward component, which is effectively preventing these error cancellation. And then, in addition to that, if you randomize the forward component as well, you can take the success probabilities of each of these circuits, the probability that you reproduce the string that you start off with, and compute a quantity that's a very good estimate of the true process fidelity of the original circuit. And this is kind of amazing, and at least I was very surprised that you could do this, because think about what you're doing in a more general context, right? You have a complicated experiment. You don't know what output it should produce, but still you're saying something about the accuracy of that output just by combining two elements, time reversal and randomization. And this is kind of, I'd be interested in thinking about whether you can also do this with analog quantum simulation experiments, right? That by combining time reversal and randomization, can you still make a statement about fidelity at the output without knowing much? Okay. So the final kind of lightning summary that I will present is this work on digitized adiabatic state preparation. So state preparation is a critical task in many quantum algorithms. This is often the first step that you do when you run a quantum algorithm. And one of the most popular ways to do this is to do digitization of adiabatic evolution. So adiabatic evolution in the analog context is just something where you take a Hamiltonian H0 and you slowly morph it into the Hamiltonian H1. So U is a control field that goes from 0 to 1 at some time, capital time T. So you see that you change the Hamiltonian from H0 to H1, and you start this state that's the ground state or the eigenstates of H0. And if you go slowly enough, the adiabatic theorem says that you should end up in the ground state or whatever eigenstate of H1 by the end of this evolution. And what you do is, because you're a digital quantum computer, is you trotterize this whole evolution. That's one way to prepare eigenstates or ground states on a digital quantum computer. Right? So you take this continuous annealing schedule and you break it up into chunks, and you do e to the I H1, e to the I H0, and you alternate between. Use standard digital quantization. So what's the error associated with this? Right? This is kind of the standard picture of what the error with the state preparation error that you should get. If you're capital T, the time that you're evolving for is very short. You should have a high error because you're dominated by what diabatic errors. The time that you're evolving for is just too short. Right? You're not really going adiabatic enough to prepare the state. On the other hand, if your T is very long, if you look at the standard first order trotter error formula, it would tell you that your errors blow up also over a large T, because your standard error trotter formula says that the trotter is basically delta T times T. So it's the smaller your time step is better, but the more steps you have to do, the more trotter steps you have to do, the larger T is, your error should grow. And that's essentially an application of the triangle inequality that gives you this. That you're just having all errors you get from each trotter step. So that's, this is not data, right? This is kind of schematic that says, if you're on the low T regime, you're dominated by diabatic errors, you have lots of error. If you're on a high T regime, you also do lots of error. But this is not actually what people see in simulation. So if you try to simulate this kind of thing, you will see that the error doesn't shoot up in the high T regime. You actually do better the larger T is. So the question is, why is it? And actually, Sameem has actually noticed this. That we had a discussion with him that he's done simulations where he's noticed this. And what we did in this paper, we derived improved error bounds, which actually explain this behavior perfectly. So the actual infidelity bound is something like this. That so this min is just forget about the one. That's just if your Trotter sequence isn't even convergent, then you'll just be in a regime where you'll have large error. But this is the key point, the true error is actually inversely proportional to capital T. So it's completely different from what the naive Trotter error bound would suggest. And this is specifically for adiabatic evolution. So adiabatic evolution, indeed, choosing large T is actually a better thing to do. This improvement from delta T to delta T squared is a small improvement that's actually been noticed previously in literature as well. So we just confirm that for this kind of evolution, but you can also confirm this numerically. You can show that the scaling indeed follows exactly this. So the message here is that this picture isn't accurate, and because adiabatic evolution is very special, the standard error bound is not what you should do. And in fact, you can explain why this happened by this nice, use this language, a self-healing mechanism. That when you trotterize adiabatic evolution, errors that you incur at the beginning of that evolution actually get cancelled near the end. And that's what leads to this. Okay. So any questions about the three of those? Otherwise, I'm going to stick to the main topic. Yeah.
So why did the self-healing happen? I mean, it is revealed through this, but why?
Right. I'm not sure I have an answer for why it happens. So the derivation of this bound is basically a perturbative analysis in the populations in the adiabatic states, and what you see is that the error is a periodic kind of behaving quantity. So mathematically, I can kind of step you through and show you why it cancels, but I don't know if I have a physical explanation for why it cancels. Right, so let me then skip to the main point, main topic. So this is quantum spied geometric data analysis. Let me acknowledge this is joint work with Akshat Kumar, who used to be a Sandian until a few years ago, but since then he's moved to other places. It's also funded by Sandia LDRD internal funding and also the QSA Center. Okay. So I'm going to switch gears completely and now talk about data analysis and machine learning. Okay, so just to set some context here, making inferences from large data sets is kind of almost a mundane task these days. Everybody does it actually. And one thing that you might not be that familiar with is that geometry can be a really powerful tool for doing this. And why is the case? The kind of high-level intuition for this is what's called the manifold hypothesis, which says that high-dimensional data tend to lie in the vicinity of low-dimensional manifolds, especially when you have this data coming from things like dynamical systems or natural laws that have conservation principles, for example, behind them. The other example to kind of think about is something like images. So, if you have an image and it's an n by n pixel image, a random n by n pixel image will basically just look like white noise. It won't correspond to a real world picture, right? Because real world scenes have more structure beneath them, which means that you're not really in this n by n pixel kind of space. There is actually a lower dimensional manifold that contains the information. And this is kind of the classic example of this, where these are pictures of somebody's face at different poses. So they're looking away from the camera, looking down, looking directly at the camera. And if you plot the underlying manifold that these pictures lie on, it's actually just a three-dimensional surface, but actually two-dimensional manifold. So all the faces looking this way or over here, all the faces looking this way or over here, looking down. And so this task of manifold learning is the task of identifying the geometry of the data set, and identifying the geometry of the manifold underlying.
All right, so this is projected down to 3D, but can we think of the original dimension to be like number of colors to the power of n times n or something?
Exactly.
Okay.
So the original dimension is n squared times in this case it's color, so the RGB coordinates of each pixel.
I see.
So it's extremely high dimensional, not too. But the information content can be compressed into two.
And when people say it's actually two-dimension, I guess it's like approximately two-dimension and not like strictly.
Yeah, it's so you could project this into 3D and you'll see a different manifold, but if there's a whole heuristic behind finding the right. There's a whole series of heuristics behind finding the right dimension to project into. And so this paper is really nice because I say it's a hypothesis because you can't, for arbitrary data sets, this might not be true, but there are ways to test whether there is an underlying manifold and the dimension.
If that ansatz is actually true.
Yeah.
Okay.
Or the notion of an underlying manifold. So this resolving this geometric structure is actually useful for many tasks. So it's being used for visualization, obviously, but also representing the data in more condensed coordinates or condensed dimensions, and also practically used for things like classification, anomaly detection, image segmentation, driving. So these are just some examples I pulled from literature where they use manifold learning to do, for example, image segmentation in medical images. I think these are like tumors that they're trying to identify. You can do obstacle avoidance for self-driving cars using this manifold learning technique. And identify protein folding pathways from MD simulations. These are like several applications of trying to understand the geometry of the data. So given that context, what are some existing methods to do this? These are some of the popular methods, and these are broadly used. The point I want to make is that several of these are dynamic methods, meaning that they're informed by physics and dynamics. And this is actually a general thing in a lot of data science. If you look behind a lot of data science algorithms, a lot of them are just motivated by physical concepts. And this is a perfect example of this. Essentially what, especially diffusion maps and Gaussian eigenmaps, maps, what these do is they rely on properties of diffusion on the data. What do I mean by that? That you have a data set here that's just each row here is a data vector. And what you do is you embed this data set in a graph. And how do you do that? Each node corresponds to a data point, and the edge between the two nodes I'll get into some more detail this in the next slide. But the edge between two nodes corresponds to a similarity between two data. So if two data vectors are close together, they would have a large or a heavy weight edge between them. Once you have this graph embedding, what you do is essentially execute a Markov process that is just diffusion on this graph. You start off at some point and you just diffuse on this graph. And conceptually, it executes a random walk on the graph, and you let the dynamics kind of discover the geometry. And physically, you can think of this as diffusion is the same as heat flow. Right? Heat flow is described by a diffusion process. And heat flow on a manifold at long times distributes that heat according to the geometry of that manifold. So if I have a cylinder, for example, and I start heating one end of it, that heat is going to distribute itself along the cylinder, not in the gap, right? And that's exactly the same thing that's happening here. That at long times, you look at the distribution of heat, the data set gives you the geometry from that. And that's the kind of physics explanation for why things like diffusion maps work. Here is the one-slide summary of the actual math behind it. It's not essential that you follow all of this, but I just kind of want to give you a feeling of what the procedure is. So as I said, you have a data set here. Vi, each Vi is a vector in Rn. That's the data vector, right? And you do this graph embedding or point cloud embedding, and this is the edge matrix for this graph, right? So as I said, each node is a data point, and the edge between two nodes is just the Euclidean distance between the two data points. So Vi minus Vj norm squared, but you embed it within this Gaussian curve. So Euclidean distances are one way of measuring similarity, but that might not be the best way, right? Because if it's on a map, if it's actually a curved space, Euclidean distances are only accurate at a small distance. That's why you embed it within a Gaussian kernel with this tuning parameter epsilon. That's a key parameter here. It's a scale parameter that dictate that you can think of it as how much do I trust Euclidean distance, right? Because at Euclidean distances greater than epsilon, this thing dies away very quickly, and exponentially decays. So it's a tuning parameter that says, what's my local neighborhood look like? How large is my local neighborhood? And so given this kernel, that sets the edge weights. And then what you define is a normalized graph Laplacian. So what does this thing look like? It's basically just identity minus this matrix, but it's suitably normalized. So these sigma matrices and these D matrices are just normalizations of that T and epsilon matrix. Okay, this is just a way to normalize the edge weights. But you can just think of it as 1 minus T. And so this is like a Laplacian, a graph Laplacian for this matrix, for this graph. And one thing to just keep in mind is that typically epsilon decays to 0 as n, the number of data points, goes to infinity. So as you get more and more data, you're densely covering this manifold, epsilon goes to 0. You can really sense it. Yeah, there's a couple of
Yeah, so it seems like the geometry is like pretty much determined by the edge weights. And then you were saying that that's determined by how similar things are. Is that kind of like fixed, or is there some subjectivity going into like when you're determining how similar data points
Right,
are?
so the geometry is not fixed by the edge weights. Geometry is fixed by the manifold that
Okay.
you're sampling from. But you don't know that a priori. You're using what you can compute from the data, just Euclidean distances. And then the task is to discover the geometry. And the next step will show how to do that. But does that answer your question? I'm not sure.
I guess I'm confused because I thought, you have a graph, and I thought the graph was the geometry.
Well, so the graph, remember the graph, this is a completely connected graph.
Okay.
Because there's a Euclidean, this is non-zero for any 2 points.
Okay.
So ideally what you want is something that, just embedded in a graph, and then if it's a 3D geometry, that graph will kind of be a skeleton of the geometry. But that's not what you will have, because you'll have connections, let's say it's a torus, for example. You will have connections across the middle of that torus. Okay. Because you have non-zero Euclidean distances. The point, if you choose an epsilon properly, those will die away, but then that will be 0. This is always non-zero.
Okay, but you're still using some way of picking whether things are similar, and if they're more similar, they're
Yeah,
they're like supposed to be closer together.
Right, so that's this Euclidean metric that you chose. You
Yeah,
could choose something else. So there is a user kind of choice there.
Okay.
But if you have the Rn data set, this is the kind of default choice nearly always. Just choose Euclidean distance. Okay. But if you have other kinds of data, you could choose something. Yeah, there.
Computing all of the edge weights, that's a lot of computation, right? It's quite expensive.
It's n squared.
Okay,
Yeah.
okay.
So this is this is, you have to do it for every ij. So it's basically, this matrix is n squared. Yeah. Yeah. So that's so okay. I'll get into the computation cost in a second. Any other questions? Okay. So given this graph Laplacian, what you essentially do is you look at the spectrum of this quantity, and the reason you do that is that, so all of this technique relies on this key convergence result, which says that this Ln epsilon, this graph Laplacian matrix that you constructed, in the limit of infinite data, it converges to the true Laplacian operator on the manifold. So delta G is the Laplace Beltrami, the Laplacian operator on the manifold, plus some order epsilon error. So this is the reason that by looking at the spectrum of this matrix, you can get at geometry, because the eigenvectors of the Laplacian tell you about the geometry, right? So by the sphere, for example, the eigenvectors of the Laplacian sphere are the spherical harmonics. So this is the key convergence results that all these techniques are relying on, that you look at the spectrum of this discrete operator that you can construct from the data, and because of this convergence result, it approximates the spectrum, and the approximation is better at the low lying eigenvalues, right? And which is what you typically care about if you want the coarse grained geometry. Okay, so is that clear at this point? Yeah.
So like, what happens if there are like 2 very plausible epsilons? Like maybe like there's a microstructure that's actually 11-dimensional or something, and like that they eventually form a bigger structure in like 3 dimension. And like,
Yeah, so there are refinements to this where you choose local epsilon. So right now I just said it's a global epsilon, it's the same epsilon for every ij, right? But you can refine this by choosing different values of epsilon in different regions of the data set. There's a lot of heuristics that work on this, but typically as n grows, there is a you could just use the smallest epsilon that you, so because of this convergence.
I guess because typically you don't have a adversarial situation like I.
Right. Yeah, that's but there's lots of refinements of this. Like this is the plain kind of diffusion maps technique that I'm but there's lots of refinements of this. People have developed. Okay, so that's all of what I said is kind of current state of the art, and this is where we started thinking about the problem. And the question was, are there other types of dynamics that are useful? So here we're using diffusion to understand data geometry, and that has limitations. So as I mentioned a couple of times, diffusion only captures the coarse scale geometry of the map. And that's essentially because there's no principled way to understand how geometry is encoded in the higher lying eigendata of that graph Laplacian. And being from a quantum information background, we particularly were thinking about quantum dynamics. And so the thing you have to first answer when you go down that road is, what is the link between quantum dynamics and geometry of phase space, of geometry of the manifold, the data map? This is not so. This is not as clear as in the diffusion case. It's not through steady state. And so let me explain what the link that we're going to exploit. So I'm going to step away from data now and just talk about continuum quantum mechanics on manifolds, though, not on phase. And I'm going to consider a Hamiltonian that's the square root of the Laplacian on that manifold. I'll explain why the square root, but maybe just bear with me for a couple of slides. But this is, so if it were just a Laplacian, it would just be free kinetic energy. So it would be the kinetic energy operator on the so if this was just flat, this would be p squared, for example. But instead, I'm going to look at the square root, and I'm going to ask what happens when I propagate according to that the unitary generated by the Hamiltonian, a perfectly localized initial state, so a delta function in position space. Okay, and what's known is that this state, when I propagate according to square root of kinetic energy, a delta function, is a state that has singular support along geodesics of that manifold in all directions. So what do I mean by that? Let's look at a quick example. So this is a circle. This is my starting point. This is my delta x position. It's a pi on the circle, and I'm going to propagate it. If I look at what this state is, it has, and this is now just writing down the mod squared of psi t. Right? It's a propagated state, mod squared. It's delta functions at pi on 2 and 3 pi on 2 when I propagate for a time pi on 2. This is what I mean by singular support. It's delta functions, and it's along geodesics because there are two directions you could go in, right? Left or right on a circle, or clockwise and anti-clockwise. So you move to both. You move to points that are distance pi on 2 away in both directions. Okay, so these are kind of perfectly localized states that just move a distance t away in all geodesic directions. In this case, there's only 2 directions you could move in. The next slide, yeah. So here, if I have a sphere, there's a continuum of directions I could move in, right? And you end up with this geodesic cone, kind of this light cone that's a distance t away from that center. So that's great. I mean, so that tells me that so geodesics are really intrinsically tied to geometry. Right? These are shortest paths on the manifold. So I should say, okay, so I've shown you that this holds, but how can I understand this statement? And I can understand it in various ways. From the math perspective, I think it's best captured in a field called microlocal analysis, which the statement there is that the wavefront set associated to hyperbolic dynamics is concentrated on geodesics in all directions. That might be a little cryptic. From the physics perspective, it's just saying that free motion of a localized massless particle travels in straight lines on math. So light travels in straight lines. From the mathematical physics perspective, as I said, H is the square root of kinetic energy or free motion. And delta X is a localized wave packet with momentum in all directions, right? Perfectly localized in space, has momentum in all directions. And so that's why it goes in all directions. And it moves according to just free motion on the manifold. And this explains why the square root is there. Square root is there because you want unit speed geodesics. If you didn't have that, you would have geodesic motion because this thing has momentum. It has unbounded momentum, right? So if you propagate it for a time t, you would end up with everywhere, because there is a momentum. Whereas when you take the square root, you get unit speed geodesics. Okay. So can we exploit this observation to extract geodesic distances and information about geometry from quantum dynamics on data? Right now, I'm going to go back to data and try to exploit this observation. So let's do, we want square root of delta G. I know I can construct L and epsilon, which from previous theory approximates for delta G. So I'm just going to build a unitary propagator that looks like e to the minus I square root of L and epsilon times T. And so here's an example. I'm going to go back to the circle, build this propagator with 2,500 samples on the circle, and let's see what you get. So the green is what the ideal propagation, right? But the blue is what you end up getting. And it's just some blob in the middle, right? It has no resemblance to the singular peaks here. And so what went wrong? It's actually the error terms that are the problem. So with any finite n, you'll always have a finite epsilon. And so these error terms mean that the propagation is no longer the geodesic propagation on that manifold. And another way to understand it is that so the finite resolution of the manifold given by a finite n and quantified by epsilon, we're asking for too much to resolve delta function propagation. Because roughly, if I construct this quantity, it resolves position space scale of root epsilon. Right? Because that's the uncertainty in coordinates that I have. And it resolves momentum up to a bandwidth of 1 on root epsilon. And what I mean by resolves it approximates the action of the true operator that I have. But in contrast, if initial states that I was trying to propagate, these delta X, are infinitely localized and have unbounded momentum. Right? So they don't lie within these kind of resolution scales that I have from the data. So we need a way to kind of coarsen the dynamics, right, to match with the resolution of that. And so being from a quantum optics background now, the natural thing to think about is actually coherent states. Coherent states are the most classical or the best approximation to classical point particles that we have, but with some finite uncertainty. So minimum uncertainty in phase space and maximum localization in phase space. So on a general manifold, you can define coherent states in a very similar way that you would do just in quantum optics on R2. In the position basis, it just looks like this. It's a Gaussian function, but with a phase that's dependent on this overlap between X and T. And as I said, it's localized to root H in space and has momentum bandwidth that scales as 1 on H. Right? So now it gives us this new parameter H to play with. Because I said that my propagator has, on the previous slide, it can resolve position space up to scale root epsilon and momentum up to bandwidth 1 on root epsilon. So now I can choose H so that I match my uncertainty, match the data resolution. So I basically need H to be greater than root epsilon. And to make sure that it's comfortably above root epsilon, you pick a tuning parameter alpha greater than 1, and you set H to be epsilon to the 1 plus 1 on 2 plus alpha. So this is this beautiful link between uncertainty in phase space and resolution that you have from data that you have from your sample. Right? This is connecting kind of a data-driven Planck's constant. Right? That your theory has a Planck's constant that's set by the amount of data you have. And the classical limit, which in physics is the H going to 0 limit, you can see is exactly the the large data limit, because as I mentioned, as n goes to infinity, epsilon goes to 0, and therefore h goes to 0. Okay, so I'm going to pause there for a second and just see if there's any questions. Comments?
Generic question, but like, did you like have this kind of scenario in mind when you first started this direction?
No, not at all.
Then isn't it kind of a miracle that like you just found a quantum mechanics kind of structure here in this problem?
Maybe we were biased because we're coming from a quantum mechanics background, but I think this notion of connecting data uncertainty to quantum uncertainty is the novelty here, and yeah, I think it is novel. I mean, it seems natural in hindsight, but yeah, maybe it's lucky or no. But so some of the analysis that goes behind this, actually, so Akshat he's a mathematician by training. He carried out most of the mathematical analysis, and that comes from a field called semi-classical analysis, which is exactly it's the kind of mathematical version of the quantum classical correspondence. So people think about what happens when you take orders of H bar and things like that. And so I think it's mostly informed by that analysis, but yeah, I don't quite know how to answer. Is it lucky or
Maybe I have
directed?
a related but somewhat different question, which I was wondering about is, to what degree is this about quantum mechanics versus waves?
Yeah.
Right. I mean, so is the data, I mean, if we don't have to think about an exponentially large data set, so we're making this into some kind of wave theory, the fact that these are probability amplitudes who cares, I mean, they're wave amplitudes.
Right.
So is there something about, I mean, in this kind of data analysis that people do, as you said, there's some, various mathematical fields where interference is sort of playing a role here. Is that what's important?
So there's nothing. I would say that the quantum ingredient. So
I mean,
I
your dynamics is coherent dynamics according to this Hamiltonian, but it's a wave equation of sorts, which propagates with this light cone in this way. So yeah, maybe interference isn't. I'm not sure if that's an important feature of this, but it's the dynamics of waves that are important. That things propagate on this light cone.
So the dynamics of waves are important in the continuum system, right? So
Okay.
the motivation was, you could think that this is wave propagation.
Right.
This is the half wave operator.
Yeah.
You're propagating a soliton or a
Right.
singularity, and you're looking at the wave.
Right. Square root of del squared.
Right.
Yeah.
But the problem is that when you go to finite data, it no longer looks like waves because everything is chunked up, right? You don't have continuum resolution.
Okay.
And so that's where the quantum mechanics is essential, because to understand the uncertainty principle that you need and how it connects to the data resolution you have, you need this picture of it as a quantized evolution. And actually so
Where didn't I get that from just Fourier uncertainty as well?
No, so you can interpret this as a Fourier. So there's a signal processing interpretation of this. So you can say, actually I have backup slides that maybe I can get to at the end on that. You can interpret this as a Fourier, but you can't derive this relation from the Fourier instance, right? This relation comes from thinking about quantizing embedding the classical dynamics with finite data in open space and propagating a quantum mechanics. So that quantum interpretation is essential to figure out what the H should be and what the relation to epsilon.
Okay, I'll pay attention to the one. See what the-
Okay. Yeah. So, okay, so that I mentioned that that's a solution. Let me show you that it works. We can construct approximate coherent states using the data again. So it's a similar construction to the continuum description that I had. You approximate these things from the data. And let's go back to the circle example. Right? So again, I've taken 2,500 points, and now I'm going to propagate a coherent state localized at pi. And this is what you get, this dotted record. So you see that it has some uncertainty, it has some width, but it's centered on the point that it should be centered on, the 3 points. Yeah.
Well, no, it's supposed to be centered on both these guys. What's going on?
No, so because that coherent state has a definite momentum. So it's not like a delta function which has momentum in both directions, right?
Okay,
So you have to put in a momentum, and so in this case we put one in one direction.
okay. So if you were using this, you would then randomize over the moment.
Right. You could pick different. Yeah, I'll show you how we apply it. Yeah.
Cool. Awesome.
So yeah, so giving it the right coarsening gives you back the dynamics that you want. And so this is captured by what we call a discrete quantum classical correspondence, which is kind of captured by this diagram where by approximating the correct quantum operators and quantum states from the data and setting H appropriately, we show that it's possible to approximate geodesics from the data. So what do I mean by that? The data, remember, is coming from some manifold. What we're interested in is reproducing the classical flow, classical geodesic flow on this manifold. So this point, going to this point on the classical manifold. How we do that is we define this data-driven quantization procedure. Basically, these operators that are defined in terms of the data, and then we do quantum evolution in Hilbert space, and then we evaluate expectation values of position. And what we can prove is that so x bar is the expectation value of the quantum propagation. Right? This is just the position operator evaluated on the propagated state. The true geodesic distance between that and the classical flow, so this point, is bounded by this H prime. So you can. This is kind of a error bond that shows that how accurate is the quantum evolution and how well does it mirror the classical evolution that you care about. And you can see again that as you get more and more data, H shrinks to 0, and this gets better. And so this whole technique comes with some rigorous convergence theory. It's not a heuristic that just says you use this. And it's the first approach to recover geodesic information from point clouds or data set with quantitative guarantee. And another nice thing is that everything is just operations on the data. There isn't a complicated kind of nonlinear PDE solving or anything like that. It's just linear operations on the data. Okay, so let me show you a moment. So I can show you some so we've applied this to kind of model data sets to show that. So that circle was the first example, but let me show you a sphere, which is this, the next more complicated manifold. So basically, this is a coherent state that's moving, and this is with 3,000 points sampled uniformly on the sphere. You can see that it moves in some direction, and the white circles, you can see those there, are the light cone. So the point is that this coherent state is still concentrated on that light cone, right, as it moves. And you can more rigorously quantify this statistically by propagating many of these and evaluating the mean error in the distance that you go. So there's two things you care about. Right? You want to go a distance t, that's the propagation time, and you want to go in the direction that you set off. And you can quantify both of those errors, and they're within the H bound that we derived here. So I told you about how to take a data set and evaluate geodesic distances between points with the data set. How do I actually use this for data analysis? Something you might care about, right? geodesic distances are actually define a similarity metric between data points. Right? So they tell you how close two data points are, and they tell you how close they are in the most natural sense under the manifold hypothesis. So what you can do is you can use the similarity metric to embed the data and to do things like visualization and clustering. So what do I mean by that? Let's say this is what we do in practice, right? We take a point J, a set sample for some manifold. You propagate from the point xj and you end up at a point xk after propagating for time t. Then what you do is you fill in this matrix which has t in the jk entry. What that's telling you is that the points j and k are a distance t away. And this is a geodesic distance. So we call this a geodesic distance matrix. And then once you have how far away all the points are, you can use that to embed in some larger dimension. So you can embed in some Rn dimension. You typically embed in R3 if you're interested in visualization, but it can be a larger Rn. And how do you do that? So I mean, if I give you n data points and I tell you exactly how far apart each pair is, you can use that information to construct a graph that embeds that data. There's several techniques to use. The one of the ways is just to actually use again, going back to the physics idea, is to think about balls and springs, right? So the spring constant is proportional to the similarity metric. The more similar things are, the tighter the spring constants will be, the closer you should push these points together. So then you just solve this n-body problem of springs and balls, and then you get an embedding. That's actually one of the classic ways to do this, but there's different techniques. Okay, so we use this to analyze a bunch of real-world data. So you can go to this paper, but there's small data sets, large data sets. I'm going to go through in more detail one of them just to show you some practical results. But yeah.
So is that ball and spring problem hard to solve in general?
No, it's not. It's not. So it's not. But it's. I think the cost is like n squared or n cubed.
Okay.
In what it ended. That's called the Fruchterman-Reingold embedding technique. That's correct. Okay. So let me. I don't have time to go into all of these, but I'm going to just go into one of these data sets. So this is a COVID-19 mobility data. So we did this work when we were all kind of locked in our homes in COVID, and so this COVID data sets were kind of the most front and center in our minds. So we thought, let's analyze one of these. And this is a social distancing data set. So what it does is it collects user location information from GPS, so cell phone GPS data, over the course of roughly 3 months, the initial 3 months of the COVID-19 pandemic. So February 23rd, 2020 to June 19th. And understanding patterns of mobility behavior can be helpful because it can tune like public health policy. Right? So are people actually adhering to social distancing measures? Where are they adhering? Where are they not adhering? Where should we emphasize this more? And so on. So that's why we're interested in that. This data is this data is a data set from this company called SafeGraphing. It's aggregated at what's called the census block group level. This is basically a block in urban environments. So in a city environment, it would be like a block. In urban environments, in rural environments, it's a larger geographic area. But you can think of it as just some partitioning of space into regions. And then what we do is we compute what's called a stay-at-home fraction for each CBG. So this just represents a fraction of devices that stayed in their home CBG for the whole day. Okay, so they didn't move away from their home CBG. And then in this data, and what I'm going to show you, I'm going to concentrate on the data set for Georgia, the state of Georgia, which has roughly 5,500 CBGs.
Right, Georgia.
Because we wanted to compare it against another paper which used a kind of a standard manifold length. I'll show you the comparison. Yeah, so it has around 5,500 CBGs. And so the data set is 5,509 by 117. Right? So it's 5,509 CBGs, and each CBG has 117 days for which you compute the stay-at-home fraction. Right? So how many people in that CBG stayed at home or in their CBG on that day? And so this stay-at-home, just for an example of, this is a time series, right? So if you look plot it as a function of date, this stay-at-home fraction for a example CPG looks like this. It just goes, up and down. And there's peaks at certain times, troughs at certain times. So what we're going to do is apply this technique to embed this data into 3 dimensions. So we're going to reduce it from a 117 dimensional data set to 3 dimensions, and then we're going to perform clustering to understand patterns in behavior. And the clustering is performed using k-means. This is what you get. So this is that embedding in 3 dimensions using the quantum manifold learning technique. The clustering is just basically separates these into points, and they're color coded by these colors. And these are meaningful clusters because if you take all the points, all the CBGs within a cluster, and then you compute their average stay-at-home time series, this is what you get, colored by them. So you see that these clusters are basically separated by the offset, the vertical offset. The patterns are about the same, right? But this is the overall degree of stay-at-home adherence that these regions have been do. And then if you go and plot the clusters, again, the color-coded back on a state of, back on a map of Georgia, this is what you get. You see this like very clear urban-rural divide, right? That in urban centers, people tend to stay at home or adhere to stay-at-home measures much more than in rural areas where it's less adhered to. So this is Atlanta, this is Savannah over here. I think, I'm not sure what urban centers are.
Look at the voting patterns, I'm sure there's that.
Yeah. Possibly, yeah. So that's what something about the standard embedding. There's a slightly different embedding. I can go over the details of this with time, but this is particularly useful for outlier detection. So when you do that, this is a different embedding that you get. And what's amazing is that you can pick up this outlier behavior, where you have this group of CBGs where they suddenly undergo a change, like a step change in stay-at-home fraction around the May 1st. And this is what I want to emphasize. This is a tiny outlier. It's 1.2% of the data. I think it's like 80 CBGs out of 5,500. Actually, less than. And it's kind of amazing that you can pick up this outlier. And what this corresponds to, so we're really curious about this. And if you look at almost every CBG in this outlier has a university in it. So we were like digging around to what happened to universities around this time. And it turns out that this is when semester ended. And so basically exams were canceled or exams were virtually done. And basically, so everybody either went home or stopped moving around at that point. And so it increased the stay-at-home fraction. So it's kind of, out of this 5,500 kind of dimension or out of this 117 dimensional data set with 5,509 points, it's amazing to pick up such a small, weak signal. And by comparison to, this is the reason we did Georgia, is that there was this earlier paper where they applied kind of a standard and current state-of-the-art manifold learning technique called Gaussian eigenmaps, where there's 2 things to note here. They got similar kind of, clusters like this, right? Similar, but maybe you could argue that some of these separations aren't as good as the ones that we got. But more importantly, they were only able to cluster in this way after embedding into 14 dimensions, as opposed to the 3 dimensions that we embedded into. And moreover, they didn't identify these outliers that we were in. So this is what we mean by this new technique is really useful for picking up fine-scale geometric structure, right, in the data set that you aren't able to pick up with these diffusion-based. Okay, so this is my last slide. So future actions. We're really interested in applying this to more data sets, really understanding both the limitations and also the potential for this technique. Also interested in further understanding this idea of quantum embeddings of classical data. So this quantum classical correspondence that I showed you, we've applied it to do manifold learning, but we think that it can be used for lots of other things, like maybe taking finite data sets and doing things like interpolation and extrapolation from finite data sets. Because essentially what you're doing is you're taking a finite data set and you're formulating a dynamical system that's linear, that allows you to move naturally in the data manifold. So let's say you only have some small amount of data and you want to fill it in with more data. You could do this to propagate to different points and think of those as kind of fictitious data that you've manufactured, find the data samples and start off. That's what we mean by interpolation and forecast. And then finally, something that we're working on right now is to try to really promote this to a true quantum algorithm. Right? So the key ingredient to the algorithm is quantum propagation of coherent states. So it's Hamiltonian simulation. And this is where we believe that there should be quantum speedups, at least if there's enough structure in the Hamiltonian. And so can we use Hamiltonian simulation, quantum simulation, to develop a quantum algorithm that does the same approach? I can say a little bit more about that if people are interested, where we're currently stuck at in this approach. But that's all I have. I'll put up a couple of papers. This is the original paper. We had recently, just last week actually, put up another paper, which is, I hope, a more than this, but we also have some additional insights into connections to signal processing in this paper as well. And the shining light on data, I hope that makes sense.
Yeah.
Thank you.
Thank you, Mohan. Some questions during the talk. We have any final additional questions? Yeah, Alex,
I'm
please.
curious, where do you get that cell phone GPS data? Like, where does that come from?
So it's from this SafeGraph Inc., which is a company that collects data.
Where do they get it from?
So
Just curious.
They so you can also find similar data sets from Google. So presumably, they build Android, and therefore they have the GPS information from every Android cell phone. I don't know where they particularly get that from. I presume they work with like cell phone providers. Yeah, it's anonymized, so you don't get user level information, but tracking.
So I'm pulled by something in this, which is you're not looking at an expectation value once, you're just looking at the state itself.
I know it is. So this is the correspondence is for the expectation value.
Ah, okay. So that's why because I was like, why wouldn't you just put like a superposition of the different momenta? Then you'll have to run it multiple times.
Right.
You're getting an expectation value at the end of it.
Yeah, so
Okay,
we did
okay.
think about doing things like squeeze states.
That was my next
things like that. But it turns out that this correspondence is hard. So we're really relying on properties of coherent states.
Okay.
To establish this correspondence.
Difficulty with quantizing this algorithm. I'd imagine that like a lot of like quantum machine learning algorithms are really bottlenecked by like the input method, right?
Yeah.
It's just
So-
the case here.
That's the first difficulty, but I'm actually willing to live with that difficulty. I'm willing to either presume there's a QRAM or just take the upfront cost of order n data loading. The thing that I'm having trouble with is so firstly, what are we trying to beat, right? So nearly all classical manifold learning algorithms, the cost is order n cubed, where n is the number of data points, because almost all of them proceed by spectral analysis or diagonalization. You might think, okay, so quantum simulation potentially could reduce this to, so state-of-the-art quantum simulation is order polylog n cost. There's an error dependence too, but in terms of dimensional dependence, it's polylog n. But the problem is that this is all for Hamiltonians with certain structure. So either sparse in the Pauli basis, sparse in some row sparsity kind of basis, and we don't have that structure with these Hamiltonians. So that's the real issue. We're trying to see if there's other ways to either reduce sparsity or other like blocking coding techniques or something that we can use to get around this. But that's the current hang.
So maybe I just can return to the question I had during the talk. I'm still a little bit puzzled about the state space we're talking about. What is n? I mean, if I'm thinking about my data set being, some unknown string of bits where I have an exponentially large space, then I can really see how I want to think Yeah, I guess
Right.
yeah, maybe I'm focused, maybe I'm fixating on the wrong thing, and so you can.
So is
you know,
the
correct
question-
me. So the question really is, to what degree is there something that is, you know, where this is really well, there's quantum inspired, as we said, it's not really a quantum machine learning approach, so to speak. But I'm trying to really understand to what degree there's what you might say is essentially quantum as opposed to just waves.
Right, so let me quickly go to
The backup side.
the backup side.
All right,
So
cool.
here is a way to think, the signal processing interpretation of what we're doing.
Okay.
Okay, so by the way, actually, no, maybe I won't. So propagating a coherent state and looking, so what we're doing is propagating coherent state, looking at the results and positions. So
Mhm.
gonna write it this way.
Okay.
But trivially, that's also this, which is propagating a delta function and then looking at it in the coherent state basis, right? And this quantity, when you look at when you project things onto coherent states, is, you know, it's a Q
See.
function if you're from quantum optics, but if you're from signal processing, it's called a Gabor spectrogram,
Okay.
because this is a Gabor wavelet. It's a wavelet. It has some uncertainty in position and so this is called the Gabor transform of F. So what you can think about what we're doing is we're doing a Gabor transform, which is a short time Fourier transform of UT applied to delta X. Okay, so and it's a short time Fourier transform because against wavelets are delocalized in time and frequency. So what we're doing by choosing H properly is we're choosing the phase space scale, phase space resolution of which to resolve the signal UT delta X. And you can see that explicitly here, right? So going back to the circle example, now I think of it as just propagating a delta function and then projecting it onto coherent states with a certain H.
Okay.
So if H is epsilon, so what I should get is this, right? Because okay, so how do I interpret this? This is saying, this is momentum, this is phase-space momentum and position. And this is saying that if I started with a let's see. I'm starting at the center and I have a certain momentum, and these are all the states that I would get to. Yeah, okay, yeah. So I've propagated for a time t. I know I should get to 3 pi on 2 and pi on 2. And all states with non-zero momentum should get to that state because it's unit speed geodesic, right? So regardless of your initial momentum, I'm going to get to position t because it's square root of delta. And so this is what I expect. This is the kind of spectrogram corresponding to this delta function picture. But if I choose an H that's too small, I get something that's completely meaningless, right? So this is this is still focused on the initial point. That's actually the blue curve. And then it's only when I pick the H that's greater than root epsilon. And so this, that you get something resembling the dynamics that the wave propagation that you want.
I see.
So, and then how do you know what H to pick? That's the key behind defining this quantization and defining the quantum classical correspondence, right? Because that's what tells you what the relationship between H and E has.
Right, so there's the going from the classical data to this model, there's a quantization there that is really quantum mechanical.
It's basically because you can only resolve chunks of phase.
Well, then I'm gonna ask a question to take up Ivan's original point of inquiry, if you don't mind, which is that just to say that quantum mechanics, just wave mechanics on discrete phase space? Or I would think quantum mechanics is more than just wave mechanics plus discretization.
Well, I think, yeah, I mean, to say what is quantum mechanics, is, you know, that's a pretty heavy statement. I think one has to qualify exactly what one means by that statement. But the inquiry, my question is, and this is an old timey quantum optics thing, is, you know, what's classical versus non-classical light, so to
Yes.
speak, right? I mean, that's one way. So one way of asking that question is, what phenomenon do I observe that I could, you know, requires me to quantize the field? And so, you know, it's kind of along those, that adversarial line that I'm writing this question, is to what degree, you know, could I do this, be inspired by an interferometer?
So it's. I would say, you know, ultimately what we're trying to do is reproduce the classical dynamic.
Yes.
But the fact that we only have a limited resolution of that object, that manifold, means that the quantized description is the quantized description with the right choice of H gives you the approximation to the classical dynamic. And so without that quantized description, you would never know what that right H is.
Right, well, I think given the time, we should conclude now. Okay, Mohan will have a more heated discussion to follow.
I don't know, to me, it's discretized, so I'm like, okay, is that quantized? 'Cause- okay.
So I mean, one of the things that I'm finding most satisfying about this is that this connection between discretization and quantization.
Right.